I want to say thank you to Black Hat for inviting me back again. I'm really excited to be talking about Android security. My name is Nick Kralovich. I'm one of the original founding members of the Android security team. I've been working in the security space for about 16 years now, 8 of those focused exclusively on Android. And during this time, I've had a really unique opportunity to watch Android mature and develop, both from a product perspective, but also from a security model perspective. I don't know how many people watch Google I/O, but at Google I/O we announced that we have 2 billion Android devices. And I'm proud and terrified to say that I have code pretty much running on every one of those. At Google, I head up the Android platform security team. Our job is to define the security model and ensure that the security model is robust. Basically, all the code that runs on the device, we're responsible for trying to make sure that the security model is sane, that we can protect user data, that we can protect application data, that your confidential data is trusted by default. And our job is also to mitigate security bugs before we even know about them. To some degree, our job is to predict the future, figure out where bugs will be. And an important part of that is attack surface management. So what are we going to talk about today? First thing I want to talk about is give you a brief history of Android security, where we started off, what we've done in the meantime to change the security model, and where we're at today. I also want to talk a little bit about our strategies for dealing with vulnerabilities. After that, we're going to spend the bulk of our time talking about bugs and specifically attack surface reduction efforts that we've done both in Android O and also previous Android versions. After that, I want to talk about some of the recognition that we've received from the security community, the future, and questions. So before we begin, I really want to emphasize that the code that runs on the device is just one small part of the responsibility, not small part, but one part of the responsibility for Android security. There's lots of moving parts, there's lots of people involved in protecting your information every day. The way I like to think about it is in layers of defense, sort of the traditional defense in depth type of model. We obviously have Google Play, which is the largest collection of Android applications in the world. We know that, and so we check those apps to make sure that they're okay. But of course, we allow people to install applications from outside, and we warn you about that. We ask you if you want to confirm the install. We check to see if the application's dangerous. And then only then do we actually get to the code that runs on the device. So again, layers of defense for at each level, reducing the probability that something bad will happen. We know, for instance, that if you install an application from Google Play, you're 10 times less likely to experience malware than if you install it from another source. So that's the idealized model. In reality, there's actually a lot of moving parts. So I'm not going to go into this sort of full graph. And in fact, this graph changes every day. This is what it looks like internally at Google. You have Google Play, we have our safety net analysis, we do analysis of applications, we try to detect badness within the ecosystem. For users who've agreed to it, we collect data about what's happening in the ecosystem. A lot of people don't know Android actually runs one of the largest antivirus system in the world. It's something I'm very proud of. But at the same time, today I really want to talk about the platform, the code that runs on the platform, the defenses that we have on the system to keep badness away, and what we do on Android to make users safer. So what are our key principles for code that runs on the platform itself? The Android platform employs a very classic AIC model. AIC, for those of you who aren't familiar with it, stands for availability, integrity, and confidentiality. As I've mentioned, it's our goal to make sure that all user data remains private. All application data remains private. You should be able to trust your most sensitive healthcare information secrets to Android. And we actually have 4 different philosophies that we use to maintain the integrity of the security model. Exploit mitigation, those are the things that you hear about every day. ASLR, NX. integer overflow protections, PAN emulation, hardened user copy. These are all changes that are designed to make exploitation of a bug more difficult. I'm not going to talk about that today. We actually have quite a bit I could talk about. The thing I'm going to spend most of my time today is really attack surface reduction. One of the things I hope everybody will take away from this is that attack surface reduction is a really effective means to ensure that badness can't happen. And when I talk about attack surface reduction, I actually talk about two different areas. The first one is exploit containment. We know that parts of Android are going to get compromised. We want to make sure that we prevent lateral movement within the device for compromised components. And so it's important from an attack surface perspective to contain an application and make sure nothing bad can happen. That's also just solid engineering practices, principle of least privilege, making sure that a process can only do what a process expects to do. There's other things that we do too in developing Android. Another one of our key philosophies is safe by design APIs and interfaces. I hope everybody in this room understands that when you make the safest thing to do, the easiest thing to do, people will do it. People do not want to introduce security bugs. But the environments that we've traditionally developed for people are very prone to bugs. And so that's one of the things that we try to fix. The other one is architectural decomposition. We know that smaller parts are easier to reason about, easier to manage, and a big chunk of the work that we do is focused around architectural decomposition. So that's a little bit about how, those are the philosophies for the Android platform team, a little bit about how we actually think about Android security. But first I wanted to talk a bit about the history of where we started off at, where we got there. So let's step back in time, go back 10 years or so. Where were we at? 10 years ago, we were in a really bad place, to be honest. Windows Vista was released. It was actually the first operating system that got rid of this concept of administrator by default. And in addition, on all the desktop operating systems out there, there was no true difference between what the application could do and what the user could do. And honestly, it's still mostly true today. As a defensive security researcher, I'm actually very excited about some of the stuff that Microsoft's been doing with Windows S because of the enhancements that they've made to remove some of the administrator by default and make sure that applications are contained. And in addition, historic desktop operating systems also has this concept of the user as the administrator of the device. And so, if we know that users make mistakes, we know that the administrator account is very powerful, and so there's a lot of risk associated with that. Mobile devices were just coming out. They were primarily feature phones. The set of security issues that came up with these phones were more focused around integrity of the network, SIM cloning, that kind of thing. There really wasn't the attack surface on the device. So Android entered the picture. In 2008, we released our first Android device. And we had a really strong desire to learn from the past. What could we do different? So one of the things we introduced at the time was a centralized application store. We want to make sure that there's one place where you can get your applications, where we can funnel it and vet it and make sure that you stay safe. Application sandboxing was one of the things that we came up with. No longer is there a concept that the application can do everything that the user can do. In fact, one application in Android cannot see data associated with other applications. One of the things I'm most proud of that doesn't get a lot of credit is our choice of memory-safe languages. We really pushed Java early on because we recognized the flaws in C, and we recognized the memory unsafety. Memory corruption is an issue. So we really had a strong desire to avoid the security problems of the past. Very early on, so Android, like I said, Android was architected for security. Having said it was architected for security, as anybody who works in software knows, you're never done writing it. You're always going to go on to sort of the next stage. So while we had laid the proper foundation of how we want to develop a system, there were still a lot of things that we had to implement over time. Very early on, our strategy was to approach Android. Our strategy to approach Android security bugs is really focused on exploit mitigation technologies, ASLR, NX, fortified source. And we spent a lot of time trying to do that in an effort to make sure that we could shut down and eliminate security bugs. What did the early days of Android look like? Well, we had application sandboxing. We were contained applications. And we had some isolation of other components with Android, but it wasn't as great as we hope. The architecture was still developing, that kind of thing. We had a global root user that was unconstrained. So if you could find one bug somewhere, then you would be able to pop users. I remember talking with a guy named John Sawyer. How many people have heard of that name, John Sawyer? Nobody? Okay. I remember talking with him, and his favorite tool for analyzing security issues or finding security issues was grep. And we wanted to make sure we moved beyond that. So we had this global root user that if you popped it, then you're in big, the entire system was compromised. The IPC boundaries, they were sort of ad hoc. We were sort of still developing them. And there was no real auditable security policy. But we reused a lot of the technologies. Our strategy has always been to reuse a lot of the technologies that are provided by modern day Linux to make sure that we could protect the integrity of the system. Obviously, address space separation and isolation has been there for decades. UID controls, we actually introduced the concept that an application runs as its own separate user. Unix permissions, stack capabilities, all of that. But something really interesting happened right around September 2011. Stephen Somali published this paper titled "The Case for Security Enhanced Android." And what he did, published a paper and a presentation. I encourage you to read it. What he did was he actually looked at 7 rooting vulnerabilities and talked about how, if we had had a mandatory access control model, these vulnerabilities would have been constrained and mitigated. So this was sort of a revolutionary moment. This was a moment where we actually switched from exploit mitigation as a primary strategy to exploit containment, attack surface reduction, trying to make sure that all processes on Android were really minimal. So we launched the initial version in October 2013. By October 2014, we had a fully enforced system where we had a mandatory access control model where each part of the system was minimally privileged. And it was very successful. I remember hearing about what at the time was a zero-day vulnerability in the Valdi asec create command. This was known in the research community to some degree. When we rolled out the 4.4 implementation that was only partially implemented, we saw immediately that shut down this zero-day vulnerability. It was blocked in several different ways. Data local temp access was disallowed. There was no symlink following allowed. And so obviously we published a patch, but we actually sort of proved out the concepts that this was an effective strategy for containing security bugs. We're never going to be able to fix all of them, so we're going to try to contain them and make sure they can't spread. So what does modern day Android security look like? I borrowed this from the Keen team's presentation. I hope they're not going to mind. Every process in Android is now contained. That includes UID 0 root processes. In Android today, there is no global root user. To say you've rooted an Android device means that you've popped the kernel. Even if you have vulnerabilities like Dirty Cow, which allows a complete compromise of user space, you're still constrained by what those applications can do. In fact, I've talked with a lot of researchers who are quite frustrated that they could get access to every user space process, but they were unable to use that access to establish persistence on the system. We have the security of least privilege widely deployed. Every process on Android only has the capabilities that it needs and no more. And we have an auditable security policy. We can actually anybody can pull the policy from the device, look at exactly what the capabilities are, and understand what the components are, how the components interact with each other. And one thing that not a lot of people are aware of, is that for most of the critical processes on Android, all code that's loaded into memory comes from provably signed, cryptographically verified sources. The combination of SE Linux and a technology called DM Verity controls what files can be loaded and prevents the introduction of new executable pages into memory. It's a very powerful technique where we can show that anything mapped into memory comes from a cryptographically signed source. That's not true across all processes, but it is true across all of the critical processes. Looking at it slightly differently, you can see we have multiple users within Android. We have Google Security Services, Google Play Protect, which is designed to add robustness to the security model. We have every process that runs the system and every UID 0 process within its own constrained, isolated sandbox. And we even have things like Trust Zone, where we protect the integrity of cryptographic keys, obviously the kernel, and hardware support for that. So this is sort of where Android's at today. But that's sort of where we're at. And this talk is really about attack surface management and things that we can do to prevent the introduction of security vulnerabilities. So I actually want to talk through a few examples of situations that I think went right and really demonstrate why attack surface management is important. As often happens, one day I woke up and I was grabbing my computer, rolling out of bed, and I look at ZDNet, and I start seeing this article. This is the way I discover a lot of security vulnerabilities, unfortunately. And so there was a security researcher at Google, really bright guy, started running a fuzzer on Linux systems. And he found a flaw with something called DCCP, Datagram Congestion Protocol. So my first notice of it was through ZDNet. And so we started our incident response process, and we started treating this like we would treat any other bug. And something really interesting happened. So we started analyzing it. I mentioned that every process is constrained to the minimal set of privileges. And that's true for access to network sockets. Applications on Android are only allowed to access a whitelisted set of socket types. Netlinks route sockets, ping sockets, TCP, UDP sockets, sort of the standard things that you would want. And we actually enforce this at compile time. If you try to add a policy that allows access to additional socket types, Android won't even compile. And we have additional testing and other things like that. But one of the things that you notice is in this never allow rules are compile time assertions for security policy, we actually explicitly disallow DCCP sockets. So this was nice. It was nice. First of all, other work we had done made sure that that code wasn't even compiled into the kernel, which is always a great thing to talk about. Even if it had been compiled into the kernel, it would have been inaccessible to any other process within Android. So here we had an 11-year-old Linux bug that we rated NSI, not a security issue. Some people say, hey, Nick, your team dodged a bullet. The way I like to think about it is, well, we didn't really dodge a bullet. We knew that there's a statistical probability of bugs happening, and by reducing attack surface, we're reducing our probability that this bug will get impacted. So how many people here have seen The Matrix where they're like walking around like this, dodging bullets? To some degree, I think that's what we're trying to do. So I was very proud of this. Not only did the whitelisting of sockets prevent that particular bug, it also prevented a number of other bugs. There was a socket family called AF, MSM, IPC sockets that were failing to do an appropriate access control check. The fact that we were disallowed creation of those sockets made those bugs inexploitable. So one solution, lots of bugs that were addressed by it. These were all bugs, we rated them high severity, but at the same time, they're not critical because it requires an attack chain length of greater than 1. It's not directly reachable. Again, I woke up one morning, found a security bug. Pwn to own. Ubuntu Linux falls on day 1. So if Ubuntu fails, if a Linux kernel bug fails, we start our response process and make sure that we're addressing it. And again, we start looking into this. This time we didn't get so lucky. It is compiled into Android kernels by default. It does require capnet and min. And a lot of processes on Android have capnet and min. But then who specifically can create those socket families? So we pulled the security policy from the device and found that it was only reachable to one process on Android. In this case, it was the netmanager D process. And so that process itself is very tightly locked down, has very limited IPC interaction. So while we classify this as a high severity vulnerability because it is a real bug, we want to make sure we have defense in depth. The odds of this bug ever getting exploited are next to none because it's just effectively not reachable. So those are two sort of idealized cases where the control of attack surface made sure that bugs weren't reachable. Careful attack surface kept these bugs from being unreachable. And so it's a really powerful technique, and it's something that we apply universally to Android, but I hope everybody here will apply it to the work that they do. So we talked about a few examples, and I wanted to give you some of the things that we've done over time in Android to really make sure that the attack surface stays minimal, that we're carefully managing the attack surface and reducing the kinds of bugs that could happen. One of the big projects that we undertook for Android O was this project called Project Treble. So what is Project Treble? At its heart, Project Treble is designed to provide strong architectural separation between core Android components, things that the Google team creates, and vendor customizations. And it was created because vendors gave us constant feedback that when a new version of Android came out, it was really hard to upgrade because a lot of things changed. They had to change a lot of their code. So what we wanted to do is provide a stable vendor API, which is represented as sort of orange there, that'll define clear boundaries between what our code expected and what vendor code expected, and to make sure that we could revision those APIs so that we could upgrade the Android OS framework portion without upgrading the vendor implementation. Now, obviously, this is important for updates. If we could upgrade the Android OS portion, we could address or mitigate bugs in different ways. Updates are incredibly important, but I also want to talk about the attack surface management that we were able to get out of this project. So what happened in Project Treble? Well, a little bit of background. Android has these things called HALs, hardware abstraction layers. And these HALs typically run in process. And so in this case, we have the orange boxes, HAL 1, 2, up to N. What's wrong with this picture? It turns out that all those HALs are overprivileged. They have all the access to capabilities that are within the process itself, even though it's not needed. They're very, very constrained in what they do. And that requires also that outer process to be able to access directly the kernel interfaces that are exposed to the hardware. So Project Treble moved these to separate processes. So now we have the one process, and it makes IPC calls to these different HALs. Each one of these HALs is separately constrained. We have architectural separation, architectural decomposition, and minimally constrained, and we have strong IPC mechanisms that we can control. And then only those components can directly talk to the kernel interfaces. So each HAL runs in its own sandbox. It's limited to the capabilities that it needs. The calling processes no longer require those capabilities. And it actually forces the attacker to perform a longer chain to get to the vulnerable kernel components. Specifically, one of the things I was very excited about is we have this process on Android called System Server, which manages large chunks of the security of Android. We were able to move 20 HALs out of System Server, reducing the capabilities that System Server had, so in the event that that's compromised, we can better constrain what that process can do. Something I was very excited about. No talk would be complete, no talk at Black Hat would be complete without talking about media server hardening. First of all, a little bit of background. I don't know how many people here remember 2015, mid-2015, there was a series of bugs called the stage fright bugs. It was a series of integer overflows within the media server code. We had designed media server with architectural containment in mind. But over time, processes grow up, things acquire more capabilities, and just sort of naturally things evolved. And so more features started developing. At the time, 2 years ago, it actually generated a huge amount of press because of the exploits that were in. But it actually turned out to be one of our most successful failures. I don't know how many people have seen Apollo 13, the idea that the lunar craft was going to orbit and something bad happened, and they were able to successfully recover it. And in some ways, I think that stage fright was our successful failure, was our graceful recovery. 2 years later, we're still not seeing any bugs associated with this. We know the containment model is working. People predicted the end of the Earth. We actually are keeping people safe. How did we do that? I encourage you to view my last year's Black Hat slides for more technical details. But conceptually, we went through and separated the media server component into lots of different components. And one of them is the extractor service. And we designed the extractor service so that it actually had minimal capabilities because it handled some of the most untrusted content. I actually want to say thank you to Marco right over there, who actually did a big chunk of the media server hardening work. I think I'm really happy about it. But we went through and we actually architecturally decomposed it so that each one of these services is within their own security sandbox and has the minimal permissions that it needed. So that was something that happened in Android N. One of the things I wasn't able to talk about last year that I'm very excited about is our use of a technology called setcomp. Setcomp, for those of you who aren't familiar, stands for the system call filtering interface. And what we were able to do is realize that these processes are actually have very minimal system call needs. And so we went through it and we said, well, what system calls are actually needed? What system calls aren't needed? And we found that depending on the architecture, we could eliminate 87 to 89% of the system calls that are available with no loss of functionality. And this is one of the great things about attack surface reduction. There's a lot of stuff that the system provides that you just don't need to have. It's just all liability, no benefits. So we did that. There were other changes that we made too. I don't want to go into a lot of details. We introduced signed, unsigned overflow detection. So we realized that integer operations in C, actually integer operations period, have counterintuitive behaviors. You end up with rollovers. It's true for signed, unsigned. For unsigned, it's defined behavior, but still counterintuitive. We just said we're going to make those hard errors because that's where we saw a lot of these bugs happen. We removed the ability to introduce new anonymous executable memory into these media server processes. So that prevents somebody from creating a small ROP gadget which goes through, marks some region of memory, read, write, execute, and starts jumping to it. Forces the attacker to have much longer ROP chains because they can only reuse code that's in memory. They can never introduce non-signed executable code into memory. And I mentioned before that we have DM verity protections, which ensure that code that's loaded into memory comes from cryptographically signed secured sources. The results were really impressive. Vastly improved architectural separation. It was easier to reason about these processes. We could create stronger sandboxes with tighter IPC boundaries. And the containment model is more robust. The Project Zero folks, who are great folks, they actually put together a blog post. And they basically said, I started working on an exploit for media server, and I got frustrated. This stuff is hard because of the constraints that we put in place. And so as a defensive security researcher, these are the kinds of things I'm really excited about. But let's put some numbers behind it. One of the things that we did was to actually take a look at bugs that came in. and see how they actually impacted our evaluation of those security bugs. And so right off the bat, we looked at these bugs and we said 23.8% of them are no longer even a security bug in Android because of the additional mitigations that we put in place. 3.2% of them had a lower severity because of the lack of reachability, because of the containment models that we have in place. So you talk about reducing security vulnerabilities by 25%. That's huge. So it was something I was really happy about. An article came out that talked about how Google rebuilt a core part of Android to kill the stage fright bugs for good. And so I'm actually really hoping that this is the last presentation where I'll ever talk about stage fright bugs again, because they're pretty much gone. So I'm very excited about that. But like anything, we continue to evolve. I mentioned Project Treble. The media server processes continue to evolve. We realized that even things like the audio server component or the camera server component still had more capabilities than we were comfortable with. Project Treble forced us to start separating those into multiple security boundaries. So where before the audio server, camera server would have direct access to the kernel, they no longer have direct access. An attacker who wants to exploit this is now forced to go jump through multiple hops. And again, our goal is to make sure that we know vulnerability is going to happen, and we want to make sure that a vulnerability in one portion is constrained and the lateral movement is protected in the devices to be able to manage the security model. What's another thing that we did in Android O? So there's this great thing on Android called WebView. It actually renders a lot of web pages. WebView traditionally has a very large attack surface. It's written in memory unsafe language. It has a history of sort of having security bugs. And we recognize that. And we want to make sure that we had a good containment model. Originally, going back in history a bit, KitKat was shipped with a hard-coded WebView in it. It wasn't updatable. In Lollipop, we actually made this updatable through Google Play because we recognize that this is a very vulnerable attack surface. But at the same time, it was still running with the capabilities associated with the Android application. And so if you pop WebView, not only do you compromise, if you pop WebView within the application, you compromise all the application's data. And so we said we can do better than this. And so one of the things that we did in the Android O preview was actually move WebView to its own isolated process. So this is what it looks like today. You have a very small stub which runs in the application, but we actually make an IPC call to a different render process, to a different web process. The process itself has no ability to access your application's data, has no ability to compromise it. In fact, it can't really even write to any files on the disk. Our separation, UID separation, our mandatory access control model, they don't allow the opening of any file except for ones that explicitly have been passed to this particular process. It also makes applications more stable, which is really nice. If it crashes, it doesn't take out your entire application. And so this is, again, something I'm very excited about that's coming out in Android O. We actually had it enabled in Android N on an opt-in basis, but it'll be the default for Android O. Again, attack surface reduction, creating containment, making sure that bad things can't happen. Let's talk about the Linux kernel, one of my favorite areas to talk about. So I mentioned before that we have really strong user space separation of processes. However, if you're able to compromise the kernel, you end up with a situation where you can regain the sort of global root access. So the kernel is very important. It's the implementation of our security model. And so something interesting has been happening over time. The kernel itself is a new target for vulnerability research. So if you look at 2014, only 4% of the bugs that we got reported, that were reported to Android, were kernel components. 9% in 2015, 39% in 2016. And people realize that the kernel, that the kernel is important. And why are we seeing more kernel bugs? I mentioned before, in user space, there is no concept of a root user. No process on Android has the ability, for instance, to modify the files in the system partition. That not only are those cryptographically verified, they're held intact by the security model. So any user space compromise can't do it. Similarly, so root on user space root on Android just isn't that powerful anymore because of the attack surface reduction that we've done, because of the containment models that we put in place. 2016 was the very first year that SE Linux, our mandatory access control model, became 50% of devices. It's probably 70 or 80% of devices now. And so, again, this is one of the reasons why people started attacking the kernel. Also, because of the privileged processes, privileged location that the kernel maintains, we actually pay more money for those vulnerabilities. Generally speaking, all kernel bugs are high or critical severity. A big chunk of the severity calculation depends on the reachability or not. Critical bugs are directly reachable by a process. High severity vulnerabilities require that you chain through a different process to get there. So there's good money here. People are starting to look into it more. It's more and more of a concern. So we looked at the kernel bugs, and we said, where are the kernel bugs happening at? There's this there's this call called the ioctl call, which passes in a file descriptor. You pass in an arbitrary command with some arbitrary data structure. There's essentially no format to this. And so we found that a big chunk of the security vulnerabilities that we had were in ioctl calls. And actually, it depends on how the bugs are reachable, or, what code is reachable or not. Because, like I said, we handle security bugs for all parts of the system. We believe in defense in depth. We fix bugs as they come in. So we also have to break it down by how things are reachable as. There were other things too. The perf event open. We found that there was a system call that a lot of vendors would customize that led to a lot of problems. And so one of the things that we contributed, because we recognized that ioctls were a big problem, one of the things that we contributed to the upstream Linux community was ioctl filtering. On Android and now on any Linux systems, it's possible to have fine-grained filtering of ioctls to remove that attack surface, to make sure that even if there's a bug there, it's not actually attackable. So we introduced this technology. It's available for everybody to use. It's checked into the upstream kernel. I'm very excited about it. I encourage you to use it. And so what effect did this have on Android? Well, I mean, originally we found there was hundreds and hundreds of ioctl calls. However, when we actually looked at what ioctl calls were being used, there were only 29 networking ioctls that were ever used. So out of the hundreds, we were able to turn off the vast majority of them with literally no functionality loss. And so I was very excited about that. There were some very peculiar Wi-Fi sockets, ioctls, that were accessible through Unix domain sockets. We were able to turn those off because we found literally there was no legitimate users in user space. And the GPU, which is a traditional target for vulnerability research, on our Nexus 6 device, we were able to find that of the 36 GPU ioctls exposed, only 16 of them were actually used. And it's pretty consistently, we found that every GPU device that we look at, the drivers have too much capabilities, and we can reduce the exposed attack surface by almost half with no loss of functionality. So what did we do to address those class of bugs? First, there was the perf interface. We actually made that disabled by default so applications can't access it. You can still enable it through the shell user, but we're not going to see malware exploiting it. We might see it for like local routing, that kind of thing. DebugFS was another one. We just said, DebugFS, the files there are too unstructured. They leak too much information. Apps can no longer have access to it. We turned it off. The other thing that we did in Android N was we removed access to the bulk of files in /sys. There's a lot of stuff in /sys which nobody ever accesses. I counted 38,000 files. And we actually found that there was only 500 that were accessed by the Lynx kernel. We were able to do a 98% reduction with no loss of functionality, drastically decreasing the probability of information leaks between applications, drastically decreasing the probability that an attacker or a researcher is going to be able to find some bit of kernel pointer or something else there. So we did a case study on the Nexus 6. We found that with these mitigations in place, 100% of the Wi-Fi bugs would have been blocked. About 50% of the GPU bugs would have been blocked. 100% of the perf-related bugs would have been blocked by default to an application, so malware is not going to be able to exploit it ever. Generally speaking, when we look at the effectiveness of the mandatory access control model that we put in place, and we look at security bulletins that we've issued over time, we see a net reduction in severity for these vulnerabilities of about 44%, which is really impressive. I mean, if we could go and fix the entire world and get rid of half the security vulnerabilities that we know about, the world will be a much, much better place. So, you know, I'm really proud of the platform security team and the work that we've been doing to make Android safer, and I think this sort of speaks for itself. Other attack surface reduction. So we've continued over time to reduce the visibility that applications have into the system. One of the changes we made for Android N was to introduce hide PID equal to functionality. For those of you who aren't familiar, this is when you run PS and you can only see your applications, you can't see other applications that are on the system. It was originally suggested by a team called Copperhead, who does some amazing work with Android security. And it prevented what we call UI state inference attacks, where one application can infer keystrokes or other events that are occurring across the application boundary. We have restrictions around kernel module loading. We definitely have restrictions around the writing to files as sys. We want to make sure that no matter what happens, the integrity of the Android system can be maintained, it can be retained across the factory reset. One of the things we started doing for Android O was a whitelist of files in /proc. So to avoid leaking of state from other applications, we've turned off things like proc interrupts, proc stats. We found that these are just not needed, and they're leaking side channel information, and there's research papers out there that talk about how one application can infer state from other applications. We've done other things too, like the hard links. You can actually link to files within, even if you don't own them. And so we found that nobody was essentially using hard links in Android applications. So we just said, you no longer can hard link any file. Again, we're sort of a reduction of attack surface. These are some examples. We actually do changes every day, and it's hard to actually talk about all the different ones. I want to talk a little bit about the recognition that we've received from the security community. I mentioned John Sawyer. When SE Linux first started coming out, he had this nice quote on Reddit. And he said that Android devices are particularly annoying to me because many of his tactics are frustrated. So one of the things to realize is Android 5 is 70% of devices now. So, so we are getting this stuff out there. We are making people safer. What are we seeing from the security research community? There's a team called Keen Labs, which is responsible for a lot of pwn-to-own exploits. So it has a presentation that they were at, and they presented this. And they're comparing iOS to Android. And one of the things they said was, in general, between the two, iOS and Android, the Chromium Android sandbox feels stronger because it exposes a smaller attack surface. Now, I'm not an iOS expert. I don't know the security. I can't really talk authoritatively about the iOS security model, but I see people in the security space saying really good things about the work that we've been doing. So I'm happy about that. Yeah. Another way I sort of measure myself is in costs that are being, the security vulnerability purchasing community. There's a company called ZeroDM, which buys exploits, and I believe they sell them to governments or other individuals. So they actually publish a price chart that goes from about $10,000 up to $250,000. If you look way up in the right-hand corner, number 2 right there is Android. We are safer than pretty much any browser out there. We are safer than pretty much any other component out there. And my goal is to make that number 1. And so that's what I'm trying to do. So, and the price change is actually growing quite a bit, where we're seeing a doubling of price for an Android 7 jailbreak. I expect those numbers to go up. 2x increase in exploit costs. Another way I measure my success is the payoff that pwn-to-own like contests have. So one of the things that you're going to see is that the price parity for, let's say, Apple phones versus Pixel phones is about the same. And so this is some of the price lists. So what we see is parity among sort of the major operating system vendors. There's actually not that much of a difference between the iPhone and a Google Nexus / Pixel device. We do see some difference in Pixel devices versus other Android devices. And a big chunk of that I attribute to the greater attack surface that's provided on those systems. Again, keeping attack surface minimal is important to contain vulnerabilities. And I think this is actually, these prices are well deserved. If you look at historically what we've been able to do with pwn-to-own, I went back through sort of however many, 8-9 years of pwn-to-own, and I looked at whenever we had to issue a platform patch for a pwn-to-own contest. And it turns out there was only ever 1 year where we lost a pwn-to-own contest, where we had to issue a platform patch. There have been other bugs. There's been bugs in Chromium. There have been bugs in sort of Google Play. But only in 2014 did we have to issue a patch. One of them was an NFC-triggered leakage, which was a technical win because it leaked the Bluetooth address. It was sort of frustrating. Another one was a DHCP code execution, but it was only considered a partial win because the exploit environment that the attacker was able to get was so constrained. So I think we've been doing some really good work, and we've been able to address like the Chromium exploits within a matter of hours, if not days. Natalie, who's in the audience over there, hi, ran a contest called the Project Zero Prize, and they offered $350,000 on the line, and nobody reported any bugs. I would like to think that we're doing something right. I think there's a lot of reasons why that may have been the case, and I think it's debatable, what could have happened. But it's something that we just didn't see exploitation. And so we want to accelerate bug discovery. And so one of the things that we're doing, we did about a month ago, is to increase the maximum bug bounties that we're paying for Android-related bugs. So where it used to be $50,000 for a remote chain to trust zone or verified boot compromise, it's now $200,000. And remote to kernel went up 5x from $30,000 to $150,000. Because we want to accelerate the bug discovery process, we want to make sure that we can figure out what's going on. And it's one of my favorite quotes. There was a WikiLeaks, and they came out and they were talking about some of the security protections that we have in place. And they said, when SE-Linux became common, it was just too hard for implants to function. So what's the future look like? I think we could do more with SecComp. I think we can do anywhere from 20 to 40% reduction in system call attack surface. I think there's some good work there. We can continue to refine the work that happened in Treble. Do a better separation of vendor code versus non-vendor code. Make sure that that separation is stronger, the attack chains are longer. Really try to scale back some of the shared data stores that we have on Android, things like the SMS database, Photos database, where it's really exposed right now. And control system properties, that kind of thing. Anyway, takeaways. Attack surface management is one of those things that not a lot of people recognize as a security win. I think we've taken really good advantage of it. I think other people can take advantage of it too. We've been investing really, really heavily into it. We know vulnerabilities will never go away, but managing attack surface makes you understand your architectures better. Perfection is achieved when there's nothing more, when there's not nothing more to add, but when there's nothing left to take away. So, thank you.